There's an experiment I've always wanted to do using one of these. It's a tube that when you spin it around, it makes a sound, and if you spin it faster, you get a higher pitched sound. And you get a very low pitched sound, higher pitched sound, higher pitched sound. Can't spin it any faster. And the experiment I wanted to do was to put one end out of the car window while driving along at different speeds and seeing if I can get the different sounds to come out when I drive at different speeds. Thing is, I'm not allowed to drive in a car at the moment because of the Covid-19 situation, but I wonder whether I can do it on one of our routine shopping trips. And we're going to do the experiment with the tube. So I'm pushing the tube through the window and we're going to drive at different speeds. There's an area that's 20 miles an hour limit, an area that's a 30 miles an hour limit, a 40 and a 50 mile an hour limit, and that's what we're going to try and see whether we can make this thing resonate and make those fun sounds. I should point out, for safety reasons, I'm not the one driving. It's my wife that's driving on our essential trip to the supermarket to buy bananas and other things that we need. So the tube is in the window like this.
But I'm limited. I'm 20.
And here's the other end of the tube.
Oh.
Well, I can hear a small bit of noise, but I wouldn't call it a note. But we're still only going at 10 miles an hour.
Or at 20.
At 20 miles an hour, we can't hear anything. Going up to 30, I think.
Something.
Yeah, you go at the right angle, you can hear. But I wouldn't call it a note. Just
You might get it down there. You might get it down the
shut the window a little bit. Oh, that was good. That sounded good. But that was about 20 miles an hour.
Just got
to get at the right angle out the window. Okay, that's... I don't know if you can hear that. I'm fairly convinced that's close to the first harmonic. The 0th overtone. That's on at about 30 miles an hour.
Make sure we don't lose the tube.
We're not going to lose the tube, don't worry, Sigourney.
That's what she's bothered about. I don't want to lose my tube, Daddy.
I'm holding on to it tight. Oh.
Oh, we heard that.
So is it between 20 and 30 miles an hour? You can hear something. Oh.
That's personal.
That's a good one.
Where it is
That was a good one, wasn't it, Sigourney?
Yeah.
It's going down the seafront, that's why.
Ooh. Must do. Ooh. Different note. We're going at 40.
That was about 40. That's 50. Just under.
Going at about 45. Oh, yes. There it is. So we're now travelling at 50 miles an hour. We can hear it's resonating at this nice frequency here. Oh, yes, that's lovely. It's a slightly higher pitch. going at 40 miles an hour than 50 miles an hour. That was very, very peculiar. That sounds good. So that's at 50 miles an hour. So we're going to look at the different factors that affect resonance. To investigate those factors, we're going to have a look at the inside of a piano. Okay, press one of the keys further up. Okay, maybe not as far as that. Press one near the middle. Okay, that's it. And again. There you go. So this is the inside of a piano, which is a good example of how resonance works. You can see that we've got strings stretched from the bottom right the way to the top. This is an upright piano. In a grand piano, the strings don't cross over in the middle like this. They just get stretched out from the keys straight outwards. This, to save space, the strings are all stretched diagonally like this. And this big metal frame here, this big iron frame, holds everything in place and keeps those strings under tension. And they're under a tremendous amount of tension. Now what you can see is the lower strings here. If I just hold down this pedal here, are the very bassy strings. So can you see? They're the bassy strings. And at the top here we've got slightly less bassy strings. And at the very, very top we've got very high pitched strings. Now they're much shorter, so you'll notice the strings get shorter and shorter as we go further up. Along here the strings are getting shorter and shorter, and the really high pitched strings, I can't even reach inside that side. I've got to go into this part here to find them. And inside here, you can see the really high pitched strings. So the strings are shorter if they're higher pitched and longer if they're lower pitched, but also the thicker strings are a lower pitch as well. Another factor that affects the resonant frequency of a string is the tension of the string. So this banjo ukulele is currently in tune, and it's sounding rather wonderful and melodious, but I can change the frequency of these strings to change their pitch. So if I take that string there, at the top here are some tuning nuts, and I can increase or decrease the tension of the string. Another thing that affects the frequency, as you saw on the piano, was the length of the string, and that's perhaps easier to demonstrate on this banjo ukulele. If I just pluck this string, I can make the string shorter by holding down the string so that it presses against one of these metal frets. The string is now made shorter, 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 and so on. And so by shortening the string, I can make it higher pitched, or longer strings, lower pitched. Here we have a more traditional soprano ukulele, and you can see on this ukulele the 4 strings. And the reason why I'm showing you this one is because it's a bit clearer to see that the lower pitched string is thicker than the higher pitched string. You can see the lower pitched string is thicker, and then if we go for these 3 strings where they get higher in pitch, they get progressively thinner. The thickest one being the lowest pitch, then the next string being the medium pitch, and the next string being the highest pitch. These strings have the same density. However, because the string is thicker here, has a bigger diameter, and therefore the mass per unit length of this string is higher. The density is the same. The mass per unit length is higher because the diameter is larger, so there's a larger cross-sectional area for this string compared to the strings next to it. So the equation for the frequency of a stationary wave seems to be dependent on three factors. Those three factors are the length of the string, the tension of the string, and the mass per unit length of the string. But we don't know what that dependency is. So the way I've written this expression down is that the frequency f of the first harmonic, so subscript 1, is proportional to the length, and that's to the power of a, some constant that I don't know, multiplied by the tension to the power of b, again some constant I don't know, and multiplied by the mass per unit length, and that's to the power of c, some constant I don't know. And I'm going to use an approach called dimensional analysis to work out what these constants a, b and c are. And so let's start off by looking at our dimensions. Frequency has dimensions 1 over time. Length to the power of a is just a dimension of length to the power of a. Tension is a force, so that has dimensions mass, length, time to the minus 2. And of course that's to the power of b. But I don't know what b is. Now, if you need some help with dimensional analysis, can I suggest that you have a look at the Isaac Physics section A2, which is to do with derived and base SI units. And mass per unit length is therefore mass divided by length, and that is to the power of c. But what I know, and this is a key idea of dimensional analysis, is that the dimensions on one side of my proportionality must equal the dimensions on the other side of my proportionality. And so my time to the minus 1 must be equal to a time to the minus 1 on the right hand side. So what I need to do is find values of a, b and c that give me a time to the minus 1 on the right hand side. Now you'll see in this expression that the only constant that has anything to do with time is b. In order to make time have a power of minus 1, b must be a half. A half times minus 2 is minus 1, therefore b must be equal to 1/2. So if I write that into my expression, it now becomes, as you can see here, time to the minus 1 equals, and there's my time to the minus 1 on the right hand side. And I've substituted in the b here. So now my m is to the power of 1/2 and my l is to the power of 1/2. There's no l on the left hand side and there's no m on the left hand side. So I have to have something where the right hand side has no m and no l on it. You'll notice here I have an m to the power of 1/2 and I have an m to the power of c. So in order to have it so that there is no m on the left hand side, these two m's must cancel. So my mass to the power of 1/2 has to be multiplied by a mass to the power of minus 1/2 in order to cancel those masses. And that's why c must equal minus 1/2. If we look at the next stage then, where I've filled in that minus 1/2, so my m to the minus 1/2 is there, and my l minus 1 multiplied by minus 1/2 becomes l to the 1/2, I've only got one unknown left, which is a. So I need to make my lengths balance on the right hand side to cancel out. And I've got a length to the 1/2, and I've got another length to the 1/2. That means I've got a length to the power of 1 on the right hand side. And so how do I cancel a length to the power of 1? I need to multiply that by a length to the power of -1. And so that's why a must equal -1. And I can plug that in. My entire expression becomes this thing here. And I can just double check that everything balances. And I can see my time to the minus 1 balances with my time to the minus 1 on the right hand side. My length to the minus 1 and my length to the 1/2 and my length to the 1/2 cancel out. And my mass to 1/2 and my mass to the minus 1/2 cancel out. this is dimensionally consistent. If you remember, my proportionality was that my frequency at the fundamental mode was proportional to this right-hand side. Well, I now know what A, B and C are, so I can substitute those numbers in to get this expression here. I can rewrite this as an equation by placing a constant of proportionality in here, and that's where the K is. I've also tidied up the right-hand side a little bit, remembering that a half power is a square root and a negative power is a denominator. But I don't know what this constant K is. What I do know, however, is that for a string which is fixed at two ends, there is a node at each end, a point where the amplitude of my stationary wave is 0, and an antinode in the middle with the maximum amplitude. I know that the wavelength of that progressive wave that forms this stationary wave is twice the length of the string. And so I have the wavelength of what we call the fundamental mode equal to 2 times the length of the string. Why do I want that? I want that because I've got a frequency and I've got something else which has dimensions of speed. And you can just double check that. I've written it on the right hand side here. My square root of T over mu, that's the tension divided by the mass per unit length, in fact has dimensions of speed. So I've got a speed, a frequency, and now I have something to do with a wavelength. Perhaps this equation starts looking familiar, because if you remember, C equals F lambda, that's a GCSE equation, and so if what's in the green square here is 1 over the wavelength, and what's in the red square here is the speed of the progressive wave, then this equation is in fact just a more elaborate version of the GCSE equation that you'll remember from last year or perhaps the year before. In which case, if we look at our expression here in the green square, wavelength has to be L over K, and therefore K has to be a half. K has to be a half because wavelength is equal to 2L for the fundamental mode, or the first harmonic. Our equation becomes this equation here, and that equation is on your formula sheets for your A level. It's also a required practical for most exam boards to investigate this equation. So what about the second harmonic? Well, the first harmonic looked like this. The second harmonic looks like this, with a node in the middle. We now have the wavelength of the progressive wave equal to the length of the string. And our expression, if you remember, F equaled 1 over lambda times C, well, now we have F2 equals 1 over L, because lambda is equal to L multiplied by the speed of the progressive wave. Predicting what happens next, I can rewrite this 1 as 2 divided by 2, and there's a reason I'll do that a little bit later. So what about the third harmonic? Well, we have our first harmonic, our second harmonic, and now our third harmonic. We've got another node in the middle. We've gone from 0 nodes in the first harmonic, 1 node in the middle for the second harmonic, and now 2 nodes in the middle for the third harmonic. There's a series. And you can see the wavelength is 2/3 of the length of the string. Plugging that into the expression we had last time, F equals 1 over the wavelength times the speed of the progressive wave. That means we now have 3 over 2L in this term. And so a general equation can be that F, the frequency of the nth harmonic, is N over 2L multiplied by the square root of the tension divided by the mass per unit length. That equation only works for strings that are fixed at both ends. What about strings that are fixed at just one end? So here we have our series where we have our node on one end but an antinode at the other, because the string is only fixed at one end, and we keep adding an extra node into the middle as we go up these harmonics. The first harmonic, or the fundamental mode, the wavelength can be seen to be 4 times the length of the string, so the wavelength is 4L, or 4 over 1L. Why have I done it over 1? Well, you can see from looking at the series why. The wavelength of the second harmonic is 4/3 of the length of the string, and so 4/3 L. And here we can see that the wavelength is 4/5. In fact, the third harmonic is probably easier to see that the wavelength is 4/5 than the second harmonic is to see that the wavelength is 4/3. On the fourth harmonic, we can see that there are now 4/7 of the length of the string is one wavelength. We can divide this string into 7 equal parts, 1 between the first node and the first antinode, so 1, 2, 3, 4, 5, 6, 7, and we can see 1, 2, 3, 4, that's the first wave. We can do the same thing to all the previous waves to convince ourselves of this series. You can use your GCSE maths to work out the general equation. Here is that the wavelength of the nth harmonic is 4L over 2n minus 1. Double check that if you want by putting some numbers in. That expression can be put into our GCSE wave equation, speed equals frequency multiplied by wavelength, to get this expression here. Remember, this only applies for strings that are fixed at one end and they're open at the other end. So what about a string that is open at both ends? Well, in that case, the first harmonic has one node in the middle. And then we keep adding nodes into the middle in this series. And you'll spot that, in fact, this first harmonic is half of a wavelength. And so 2 lengths of the string is 1 wavelength. And here we can see we go from the maximum amplitude to the maximum amplitude again in 1 length of a string. So this wavelength equals the length of the string. This series should start looking familiar because it's the same series as when we had fixed ends of the string, but now we have open ends of the string. Now the reason why this case is interesting is because this is the same as our Whirly tube. Our Whirly tube was open at both ends, and so our wavelength of whatever harmonic sound was being produced is going to be equal to 2 multiplied by the length of the tube divided by the harmonic of the sound we were hearing. In other words, our expression for the frequency of our nth harmonic in our Whirly tube is this. Well, we can test that because we recorded the sound coming from our Whirly tube. All I have to do is measure the length of the Whirly tube. I know the speed of sound in air, and I can work out what harmonic of frequency I was listening to. So here is some mathematics that I've done. The speed of sound in air is approximately 330 meters per second. The Whirly tube, I went outside and measured it. It had a length of 74 centimeters, which I will call 0.74 meters. And using the series we had before, I get a first harmonic frequency of 220 hertz. I have a signal generator here, which I'm hoping the microphone picks up. 220 hertz sounds like this. Well, let's hear what the second harmonic sounds like. The second harmonic was 450 hertz. And that sounded like this. In fact, that is what the Whirly tube sounded like. We also have the third harmonic, which sounded like this. That's 670 hertz. And the fourth harmonic at 890 hertz sounded like this. Faster. And so in fact we did hear from our Whirly tube these 3 pitches. But why was the Whirly tube making sound at all? And why did going at different speeds cause us to change the harmonic that we were listening to? Well, that's due to an effect called resonance that you will study in a little bit more detail when you look at simple harmonic motion. But you might want to look up why it is you get sound from the Whirly tube at all.